Hello everyone. Today we are going to understand about a simple CUDA program that performs vector matrix multiplication using GPU parallel computing. This program multiplies a matrix A with a vector B to produce a result vector C, and it runs this operation on GPU using CUDA programming. Now this matrix multiplication is carried out using a mathematical formula, that is C of I equal to sigma j equal to 0 to n minus 1 A of I of j into B of j. This is a basic matrix vector multiplication where A is a 2D matrix of size n into n and B is a 1D vector of size n. Now let's break down the code. And the first line says hash include iOS stream. This includes the standard input output library for printing results. And this is the main code. And we write a function called global void vector matrix mult of const float A, const float B, float C, comma int n. This is a GPU kernel function that runs on the device GPU. It's launched with many threads, each computing one element of vector C. And the next line says thread index calculation. And for this we use a line called int I equal to block idx.x into block dim.x plus thread idx.x. This computes a unique thread index I across the entire grid of threads. And to multiply row of matrix A with vector B, we use this block of code that says if I less than n, float sum equal to 0.0, for int j equal to 0, j less than n, j plus plus, sum plus is equal to a of I star n plus j star b of j, then c of I equal to sum. This block of code explains if the thread index is valid, each thread computes the dot product of the ith row of a matrix A with vector B, and this stores the result in C of I. Now we enter into the main function float star A comma star B comma star C, and we have declared these variables ABC using pointers, and now we allocate memory for these variables. A equal to float star A malloc n into n size of float, B equal to float star malloc n into size of float, C equal to float star malloc n into size of float. This allocates memory for matrix A and the vectors B and C on the CPU. Now we initialize the variables using the for loop. For int I equal to 0, I less than n, I plus plus. For int j equal to 0, j less than n, j plus plus. And a of I star n plus j equal to 1.0 and b of I equal to 2.0 and c of I equal to 0.0. Matrix A is filled with 1.0, vector B with 2.0 and result vector C with 0.0 initially. Now we allocate the GPU memory for these variables in the device. For that we use a command CUDA malloc ampersand d n into n size of float and CUDA malloc ampersand d of b comma size into c size of float, CUDA malloc ampersand d of c comma size into float. Now these three lines will allocate memory in the GPU for matrix A, vector B and the result C. Now, in the next line, we copy the data from the host to the device. For that, we use these commands. CUDA memcpy d of a, comma a into n size of float, comma CUDA memcpy host to the device. And CUDA memcpy d of b, comma n of size of float, comma CUDA memcpy host to device. The initialized matrix and the vector are copied to the GPU now. Now to launch the CUDA kernel, we use int block size equal to 256, int grid size equal to n plus block size minus 1 backslash block size, and vector matrix mult less than grid size comma block size greater than d of a comma d of b comma d of c comma n. The kernel is launched with enough threads to cover all n elements. Each element thread computes 1 of c of I. Now we wait for the GPU to finish. Now for that we use a command CUDA device synchronize function. This function ensures the CPU waits until the GPU finishes the computation. Now copy result back to the host. For that we use CUDA memcpy c comma d underscore c comma n star size of float comma CUDA memcpy device to host. The vector c is copied back from GPU to CPU to print the output. Now let us see the print statements in the final stage. Print A, printf C, printf B. This prints the input matrix A, vector B, and result C. You can verify the multiplication manually from the output. Now, the final command of this code is CUDA free D underscore A, CUDA free D underscore B, CUDA free D underscore C. So, always after using this GPU programming, we have to clear the memory from the GPU to prevent memory leaks. So, the conclusion of this code is this code program shows how we can speed up matrix vector multiplication by using parallel threads on GPU. It demonstrates memory allocation, kernel launches, thread indexing, and data transfer between the host and device. So, this is the video. Thank you.